All right, welcome everybody to our ASPEN Net seminar series. I just wanted to mention before we get started that we have a town hall that's coming up on June 1st as part of Quantum 2.0. So you can go to our website to register for that. And part of this tutorial series, part of this town hall, it's all building to this platform that we're trying to build, this ASPEN Net platform to really go after these all optical quantum repeaters and kind of metropolitan scale quantum networking. And, it takes many people to do that. And so we need as many voices and participants and people to kind of help us build towards this vision. And this town hall is a way that we're hoping to get everybody into one place together to talk about that. So it's coming up June 1st in conjunction with Quantum 2.0. So if you're interested, please register. I believe we still have some spots available. So we're going to turn it over to our speaker for today, Michael Raymer from the University of Oregon. And Mike's accomplishments are far too numerous to list here. Not only has he been someone who has inspired many people, including myself when I was a graduate student in this field, um, but he's also played a large role in the development of um, the the National Quantum bill that was the NQI that was passed by Congress. He was one of the architects of that and has played a huge role in quantum information in the US and quantum optics. So I'm going to pass it over and we're going to hear about quantum sensing applications, in particular quantum telescopy. So take it away.
Thank you, Krister. Hey, everybody. It's a pleasure to be here. It's a pleasure to be involved in this ASPEN Net effort. See what we can do with a quantum network in the near to far future. So I'll be talking about quantum telescopy using single photon path entangled reference states. And my co-authors at the University of Oregon are Matthew Brown and Brian Smith, who is the PI on the ASPEN Net grant, and also Marcus Allgeier, who is now at the University of North Dakota. Okay, so ASPEN Net is the attosecond synchronized photonic entanglement network, which is a funded grant from the National Quantum Virtual Lab program. And the participating partners are listed below. So a take-home message of this talk is a well-known fact that with path entanglement, the data rates for collecting quantum data can be higher because only one photon is needed. And this is actually, in principle, ideal for doing telescopy of very dim, distant objects like stars. However, ideal performance for these methods requires phase stabilization of network links. And phase stabilization is one of the cornerstones of the ASPEN Net project. And that's why it's called attosecond synchronized network, because attosecond is on the time scale of a single optical cycle, which is required to be stabilized across the entire network. Okay, so to take a bigger view of this area, what will a quantum internet look like? And here I show a little sketch that I made for this paper that Mark Olankar, Dirk Engeland, and myself wrote a few years ago at the request of the National Science Foundation, talking about quantum interconnects. And of course, a network is an interconnected, system of many different kind of devices. And so on the right here, we have quantum computers, which can be modular, so they have to be interconnected. We have quantum memories, which have to be interconnected to the quantum computing modules. We have quantum memories, which you can use frequency conversion, QFC, to change the wavelength of the photon signals. Then we have a network of quantum repeaters. We have users hanging off of this. We have random number generators. And finally, on the far left, we have distributed quantum sensors or point-like quantum sensors. And I'll be talking today about the concept of distributed quantum sensors. Okay, so a very nice example of a distributed measurement or sensor is the recent imaging of the black holes that was done a couple of years ago using VLBI techniques. This relies on the fact that angular resolution of a telescope is proportional to the wavelength of light divided by the aperture size. So in this radio frequency regime, this team of scientists and engineers built a radio telescope essentially the size of the Earth by placing a number of fairly large receivers in different locations, and then mixing the radio signals coming from um, objects such as this black hole, um, mixing those radio waves with a local oscillator, which is detuned in frequency, which gives you a heterodyne signal, which can be recorded electronically in a voltage waveform on a hard drive. And these hard drives then are physically moved um, to one location where they're put into a computer and processed. Okay, the question is how to make an optical telescope the size of the Earth. That's not easy. But going back to 1921, when Michelson did the first distributed optical measurement called interferometric detection, his scheme is shown on the left here. You have two optical telescopes, which are actually just apertured regions of a single larger telescope. But the point is that the separation between these two apertures can be varied, and the value is called delta Y, sometimes called baseline. And the light from the two telescope apertures is put onto a film where interference fringes are observed. As the separation of the two apertures changes, because you can move them around, the visibility changes of these fringes. And this visibility change versus aperture separation is the data from which you can use to reconstruct the intensity distribution of the distant emitting object. Well, that system is equivalent to the one on the right, where you have use a beam splitter and a controlled phase modulator, and then as a function of controlled phase, you see this oscillation here. Okay, now Sang showed that this scheme, this Michelson scheme, actually beats all others if there are no losses. But of course, in reality, when you try to extend the baseline, there are losses, and that's where quantum comes in. All right. So to do this, you need to understand one basic theoretical point about classical statistical optics, which is called the Van Zernike theorem. You can find that in Born and Wolf. And it basically says that if I have an intensity distribution of incoherent point-like emitters, say thermal type emitters at a distant star, they emit light down to these two receivers, and the two receivers are receiving signals, and they somehow can measure the 2-point field autocorrelation, electric field. And the theorem says that this is proportional to the Fourier transform of the intensity distribution with as a function of delta y. Okay, so the interference signal then can be written as 1 plus a visibility factor, the modulus of v as a function of delta y, and a cosine term. The cosine term is modulated by this delta, which is the controlled phase under your control as the experimenter. But there's also a complex phase which depends on delta y. So the complex visibility function is v and the phase phi. We want to measure both of those, v and phi, as a function of delta y. Then we do the Fourier transform, and we get the intensity distribution. Okay, all right. Now, if you only measure the modulus squared, or the amplitude of the visibility, v, then you can do an inverse Fourier transform to obtain not the intensity distribution itself, but the autocorrelation function of the intensity distribution. That's an easier measurement than measuring the full phase. Okay. Now, the state of the art in this field right now is at the Chara interferometer, in which there's an array of 6 telescopes separated by a maximum of 330 meters baseline. And here's an example of a reconstructed star intensity map, which also corresponds to looks like a temperature map. The star is called Altair. All right. Now you'd like to increase this baseline, but before we do that, let me back up a little bit and show you some of the other approaches. But just to reemphasize the point that if you try to increase the distance, say by sending one of the telescope outputs into an optical fiber, you'll have exponential fiber loss with distance. Now, historically, you're also aware, I know about the Hanbury-Brown twist experiments, which is called intensity interferometry, where you measure starlight or infrared or radio waves from into two different receiving apertures, and then you convert those into voltages, and you do a linear mixer. So you're looking at coincidence counts, but the point is that in order to see coincidence counts, you need to have one photon detected in each aperture. So this limits you to looking at bright sources. Okay, that's fine. It's a great approach if you have bright sources. The other approach that was developed in the 1970s was by Charles Towne and collaborators, in which they did heterodyne detection. So what they had was they had two apertures. They have two separate lasers which were locked together optically over some distance. They could vary the distance between these two telescopes. They had detectors, and then they again did a multiplication technique, getting a fringe amplitude. So this is a coherent receiver, and it's equivalent in some sense to the Michelson coherent receiver, yet it does not require bringing the light from the two stars physically together because you're using two separate local oscillators to effectively do the same thing. However, this system is highly limited by local oscillator shot noise. So that gives you a sort of a standard quantum limit, which you cannot beat. Uh, this is done at 10 microns, where the shot noise is significant and really limits this technique a lot, in contrast to the radio heterodyne interferometer, which is less affected, almost no effect at all of shot noise in the radio regime. Okay, so that gives you the overall picture of what's going on. Now, about 10 years ago, Gottesman, Krook, and Yenawine proposed a very clever technique, which we're now implementing in our laboratory. Is the following. You do a distributed quantum measurement. So the way you do this is essentially you use the same idea that Townes did with the heterodyne detection, but instead of sending a strong laser fields onto these two locations, you have a single photon source. And let's assume it's an ideal push button deterministic single photon source, as Gottesman did assume. You have a 50-50 beam splitter. You split that photon into two spatial paths. So this is what's called a single photon non-classical path entangled reference state. And the joke here is we call this a non-local local oscillator. We also call this a path entangled state. Okay, we have a phase controller here, delta, which we can vary ourselves to see fringes. And the fringes occur as a function of coincidence counts between one detector on the right side and either detector on the left side. If so, the idea is that you have one photon known to be emitted by your reference source, and then in the weak star limit, you have one photon from the star. But that photon travels into two paths. So you can look at this like an interferometer. The star is a source. It emits one photon, which is split across two paths. This source at the bottom also emits one photon, which is split across two paths. And then you just look at coincidence counts. So really, this is a pretty, standard kind of looking interferometer if you have two separate photon sources. But you're looking now at coincidences. However, the point is that you only need one photon from the star because you already have one on the ground. So this gets over the brightness limitation that exists in the Hanbury-Brown twist scheme. Okay. So you look at those coincidences as you vary the delta y between the two apertures. And then if you get good signal, you can reconstruct the source. I should mention on here on the left, this is a single photon temporal mode kind of entanglement, or better, probably call it a spatial mode entanglement, because you're splitting this single temporal mode into two spatial paths. And when you have just one photon entanglement, this is called single rail entanglement, because the information is either it's in the number of photons. You either have zero photon or one photon, as you can see in the state here, 0, 1 plus 1, 0. This is distinct from having two photon entanglement, which is usually called dual rail entanglement, which would be the kind of entanglement you would use to verify Bell inequalities across a large distance. But for the Bell inequalities, you don't need to control the optical paths between the source and the two receivers. Whereas in a single rail or single photon entanglement, you have to control the phase of all the paths. Okay. So moving on, what are the challenges to making this work over long distances? Well, as I just said, you need phase stability across the entire system. Now you have a long distance here, let's say at 10 kilometers. You have atmospheric turbulence, which is always an issue. You have local oscillator photon loss. Again, I'm calling the single photon the local oscillator. It's split on the beam splitter, it goes to the right, goes to the left. But for example, here you have a photon that survives, and here you're missing a photon. So this will lower the count rate significantly. Uh, each time bend contains this spatially entangled path state. Okay. And the final large challenge is number 4, optical bandwidth coverage. Because here we're interfering a single temporal mode, which you could think of as a Gaussian wave packet that has a well-defined duration and time and bandwidth, which is more or less transform limited. That's only one mode of light, whereas the star is emitting, at any given time interval and frequency bandwidth, thousands or millions of modes. And the Michelson technique, the good thing about it is that it can process a large bandwidth, say 10 nanometers of bandwidth in real time. That's many modes, thousands of modes. Whereas here we only have one mode at a time. So I'll show you later, one has to start thinking about multiplexing, which is also a very relevant topic in the topic of optical quantum networks. All right, so moving on here. So the hypothetical long-term plan would be something like this, as just one example. This is certainly not something we have built yet, but this is what we're looking for in the future. So you would have a single photon source at the bottom, the blue box here, and it would be split, and you'd have a series of phase-stable quantum repeaters, which are, using like DLCZ or some other protocol to try to extend the entanglement between the two telescopes. So you try many times, and ultimately you can you can develop entanglement between, say, two quantum memories, say the far one on the right here, this little gray box, and the far on the left here. Now notice that each of these memory slots is not storing one photon, as maybe the picture seems to illustrate, but really you're storing essentially a half of a photon on the right memory and half of a photon on the left memory. That's just a way of saying you now have entanglement in single rail form between those two memories. Okay, then the idea would be you store at your leisure. You spend a lot of time developing these stored up path entanglement memories on the left and the right, and you now have 1,000 or a million of these all stored up. And then, as it says in the bottom here, you release a fast burst in a time interval which is shorter than the atmospheric scene time window, which is over milliseconds. So instead of just sending out the photons and hoping they make it, at some slow rate, in meantime the atmosphere is drifting, you could store them up in advance and then send out a burst and get your data really fast. And then you could repeat that process many times as a function of the separation between these two apertures. Okay. And as you all know, the exponential loss with distance that typically is in optical fibers can be suppressed down to roughly polynomial loss by using matter-based repeaters and various types of distillation protocols, as shown many years ago in this famous paper here. Okay, so moving along, that's like the overall long-term scheme. Now, first, let's talk a little bit about phase-stabilized optical fiber networks. In the past 5 years, there have been probably 5 or 6 demonstrations worldwide showing that it is possible to phase stabilize long fiber lengths. It was motivated initially, I believe, by the work on atomic clocks, so synchronizing clocks. And we're shown here a nice picture from the Boulder Atomic Clock Optical Network Collaboration, also called BACON. So I'm not going to talk about the details of this because it's not that important, but the point is that you're trying to stabilize two different kind of clocks using different stabilization techniques, different wavelengths, and so on across a long free space link, and comparing that with the stabilization that can be obtained across a fiber link shown here. Now, for clocks, all you really care about is a kind of a long-term averaging, because the longer you average down, you can suppress the phase variance and the noise. That doesn't apply so much to our case, where in our case we care about short-term pulse-to-pulse stabilization. So that's even a step further in technical challenges. This is why we have the Boulder NIST team involved in the project. When averaging down for, I don't know, seconds or many seconds, you can get down to 18 digits of accuracy, which is certainly, attosecond, below attosecond. So the challenge is now to make this same kind of stabilization working for short-term pulse-to-pulse operation. Okay, it's hard. Okay, this just shows a picture from their experiment, how they transmit between the NIST building and the CU building. It's state of the art. Now it looks like my face is covering a little bit of that. Okay, I think you can remove the upper right hand talking head picture if you want to read what's in the green box. So here we as I said, we need pulse to pulse stability, which is more challenging. But just to point out that there has been a lot of work already done here and for example, without using repeaters, twin field QKD has been demonstrated for more than 200 kilometers by 2 or 3 groups around the world. So phase stabilization on cross networks is something that's feasible but challenging. All right, now back to the Gottesman scheme, and I'll talk finally about our experiment here that we carried out a couple of years ago. We're implementing this scheme. So again, here's the scheme, but in order to make the single photon pulse, we use the well-known technique of spontaneous parametric downconversion. So pulse laser comes in, think of it as a blue pulse. It generates a pair of photons. One of those is detected, called the herald. And then we know we have this other photon here, that's a signal photon. So it's probabilistic, maybe 10% of the time the laser pulse will generate a heralded single photon. So that's fine, because there's only one photon needed. Okay, so we split that and we do the Gottesman protocol, the path entangled state, and we vary the distance delta y between the two telescopes. Here, of course, we're not talking about quantum repeaters. That's beyond what we can do right now. So here's the basic setup that was carried out primarily by Matt Brown with the assistance of all these other collaborators, including John Monnier, who is a leading astronomer at University of Michigan. And that picture I showed earlier of the Chara image of the Altair star was actually done by John Monnier. So he's helping us understand what are the astronomical points of interest and technologies that they're currently using. So the way we do the experiment is a kind of a toy model tabletop experiment. We have a short laser pulse, it's 100 femtoseconds or something, and has a Gaussian transverse profile. We put it through a rotating ground glass screen to make spatially incoherent light. Although notice it's still temporally coherent because it's coming from a transform limited laser pulse. So it's a single temporal mode, temporal spectral mode, but it's spatially incoherent. And we put that through a double slit to make an interesting object. You could think of that like a binary star with a certain shape. We want to image that double slit. So the scattered light comes out. It produces a speckle pattern down here. Our two apertures are simply bare optical fibers. Each fiber has a core diameter of about 5 microns here and here. So those are very, very small telescope apertures. And obviously, using one of those telescope apertures, you could not image anything because it's too small. So proof of principle, then we send those we attenuate the laser pulse way down to the single photon level on average per shot. So that photon is split and enters both paths, these two fibers, and these detector setups, which are superconducting nanowire detectors. And as I said, our single photon local oscillator pulse, this little red pulse, is generated by heralded SPDC. Okay. This is the setup, just so you can see how it looks that Matt built up. So the TISAF laser is beam split for two purposes. One is to make the simulated star by the rotating screen, the double slit, and a nice speckle pattern, which we measured as a G2 has a value of 2, which means it's a good thermal-like source as far as the thermal statistics of the single mode are concerned. We're not looking at the spectrum of thermal light, but just a single mode of thermal light. Then we have a beam splitter, 50-50, which allows us to send part of that light into one fiber collector here, and the rest of that light in another fiber collector here. And then we can vary the separation between these two fiber tips just by moving one of these fiber tips back and forth on a translator. So those paths go into these optical fibers and hit these fiber beam splitters, which are also illuminated by this single photon heralded down conversion source. BBO doubles the light to blue, KDP down converts it back to red. We split the herald off and we go to a time tagger, and the signal gives beam split and goes into these two fibers, etc. Then we have our beam splitters. Then so we're looking for triple coincidences where we have a herald click and then a coincidence click on two of these detectors. Now the phase is varied by this PZT, moving a mirror back and forth a small distance, and we use a triangle ramp from this voltage waveform generator. So we can vary the phase linearly up and down. All right. So as the phase is varied up and down, this is phase delta versus time. The phase goes from 0 to 4 pi back and forth on a triangle. We're trying to estimate this quantity, which is V and phi. Now, delta is the phase we're controlling. We're ramping it, looking at fringes, and we're trying to estimate what the phase of the fringes is and the visibility of the fringes. Well, the estimator that you can use is the following, e to the minus I delta sub j, where delta sub j is the value of the phase at the time of a given coincidence event. So the events occur randomly. Notice, the variation of the phase is very slow. It's, tens of kilohertz. Whereas the laser pulses are coming in at a rate of 80 megahertz. So there's millions of pulses coming in here. And every once in a while, one of those laser pulses and its corresponding single photon oscillator will create a coincidence event. At that time, we simply look over to our lookup table and we see, the phase at that time was delta 1, and we record that. And then we wait for the next coincidence and we record the phase of the PZT at that time, delta 2. And if you simply take all a collection of 10,000 or a million of these recorded phase values and put them up into this exponential and do an ensemble average, you actually get the complex visibility divided by 2. And that's as a function of the separation of the two apertures. So both of these functions here depend on the separation. So you do this, tens of thousands times, then you vary the, you have to do this within a time where the atmosphere doesn't change, okay? Or the phase relations in the interferometer don't change. So that has to be done fairly fast. Okay, so in the presence of random but slow interferometer drift, you can easily collect enough data points before the interferometer drifts to extract the magnitude. But recovering the phase is more challenging. And in actual astronomy, they have various techniques for doing that, but it requires more than it requires more than 2 apertures. So I won't talk about that. Okay, so here's just one example of a reconstruction that Matt did successfully. So this shows the two slits with the intensity distribution of a Gaussian illuminating those slits, giving you these kind of knife-like looking features separated by distance d, which is known because we fabricated the slits. So we know they're separated by 2 millimeters, and we know what the slit width is. So Matt did the experiment. He varied the distance between the two fibers, which is telescope displacement in millimeters. He collected enough data to measure the visibility, the magnitude of the visibility as a function of the telescope separations, and he plotted it, and it looks like this. And of course, it oscillates because this is a fourth order interference, um, but of course, it oscillates because there are two slits. And the oscillation pattern here is a reflection of the shape of these slits and the separation. So as I said, if you Fourier transform the magnitude squared, this yields the autocorrelation function of the intensity distribution. And since there are two peaks in the intensity distribution, there are three peaks in the autocorrelation. And you can see here that a theoretical fit, which is basically the Fourier transform of this function, is shown as one of these curves. I think it's the dashed curve, yeah. And the numerical Fourier transform of the recorded data is shown in the other curve, and the error bars are so small you can barely see them on the screen here, and the fit is essentially perfect. So that's showing a very nice result. This is where Matt published this result. Okay, so that was the basic idea, and next generation of the experiment is to try to look at starlight. So we've been joined by Francesca Sansavini as a postdoc researcher in the group. This is our physics building. And on the top of the building back here, Matt worked for a while to install a telescope dome, which is pretty remarkable. This is a high, you can say high quality amateur type telescope dome. It's about, 12 feet across, sits on the roof here, has a rotating dome, telescope inside, and so on. And then there are optical fibers that take the recorded light from the star or the sun down a few floors into our laboratory. That's the plan. But now here's what the challenge is. Beyond simply all the other challenges that I mentioned, we have the challenge of matching the temporal modes. Okay, so at the bottom right here, we show the heralded single photon wave packet is in a single temporal mode, single temporal spectral mode. You can think of it like a Gaussian Fourier transform limited wave packet. So we know what that is because we designed it and we built it. But the starlight is stationary and broadband. So you need to filter it in both space. Well, space is filtered by the fibers, and then you need to filter it in terms of spectrum. And we're designing it now for a spectral filtering bandwidth of 3 gigahertz, implemented by perhaps fiber Bragg gratings. And then we need to have fast photodetectors, which ideally would be number resolving, but we're using superconducting nanowires, which now are not number resolving. And we can easily achieve less than 100 picoseconds of a timing resolution. So the bandwidth time product is less than 1. This means we are approximately picking out a single mode in space, frequency, and time from this starlight. Okay, and we're getting very close to having that setup working right now. But beyond that problem is the problem, as I mentioned earlier, which is the bandwidth coverage. So as I mentioned, in the direct Michelson type scheme, you can easily process a bandwidth, maybe say 10 in the nanometers, around 1 micron of wavelength, essentially looking at, sort of like white light fringes. But in our technique, we only look at one mode at a time. And if you think about starlight, if you tile the plane of frequency and time in terms of modes, say, for example, 3 gigahertz by 145 picoseconds, well, starlight is very sparse. At 5,000 degrees Kelvin, I think the occupation number of a single mode is something like 0.01. So 1 out of 100 of these little modes will be occupied by starlight. On the other hand, you need to fill every single one of these modes by a local oscillator because you're really not looking at photons that come from the star. You're just measuring the field properties. It's a quantum field. You can't say that the star photon arrives here or now or later or there or there. You're really looking at quantum statistics of the field. So you need to flood all these modes with local oscillator photons. So they're like event ready whenever the star decides to allow you to measure a coincidence event your local oscillator has to be there. So in future generations of this scheme, you would have to do massive frequency and time multiplexing. So time multiplexing just means run everything at a very high rate, say, gigahertz pulse rate, or yeah, roughly. Spectral multiplexing means that you take advantage of the fact on the far right lower corner here, this SPDC source emits broadband heralded photons. And so there's the idea of frequency demultiplexing and multiplexing. So the idea is that you would have a frequency demultiplexer here and hundreds of nanowire detectors, which herald a signal photon over here in a particular frequency and time bin, one of these little bins here. And you can have hundreds or thousands of different frequency bins because the down conversion can be designed to be very broadband. We're working on the theory of that within another context, which is the Center for Quantum Networks is another project that we're collaborating on, and we're working on the theory of spectral multiplexing of down conversion and heralding that. So the idea that you would split that, and then you would send that to your multiplexed detector setup. So you have again, it's two telescope apertures, and each one of those would have to have frequency demultiplexing. The local oscillator would have to be frequency demultiplex, and then you'd have to have an array of thousands of balanced fast photon counting detectors. So this is obviously a very large challenge, both scientifically and technologically, but this is the direction that one has to push in. Okay, so that's it. The future is kind of like the following. We know that the quantum advantage of this system is that using a repeater chain allows you to beat the exponential fiber loss with distance. That's an important point. It's not that quantum entanglement magically gives you, super resolution, like, like Noon states or something like that. And it doesn't give you like 1/n Heisenberg scaling or any of those famous things. What it simply does is if you have a good repeater chain, it allows you to transmit the local oscillator photons across very large distances with only polynomial loss in distance as opposed to exponential loss with distance. Okay, but if you can do that, then there are a lot of applications which I don't have time to talk about for this kind of technology. So in order to win, we need the following things: a working repeater chain, a phase-stable network, increased heralded single photon rate and faster detectors, and large numbers of detectors to allow massive multiplexing with the reference states. Okay, and this paper is here again. Our paper is there. Okay, so finally, I'll just reiterate what Krister said about the ASPEN Net Town Hall. If you're interested in that and not already signed up, you can scan this QR code or go to the ASPEN Net webpage. Just search ASPEN-net. You'll find the webpage. Okay, well, that's it. I'm going to stop there.
Hey, thanks, Mike. So we have plenty of time for questions. So if folks have any questions, just feel free to unmute and ask your questions, or you can put them in the chat and I'll read them.
Hi. This was a great seminar. I really enjoyed it. A great tutorial. I did have a question though about the interferometry that's happening, say in the particular telescope that is seeing the two counts in the detectors. So these are happening simultaneously in time. I'm just wondering about the Hong-Amandel effects. Did that enter in at all to what's going on here, or is that completely different?
Yes, you could say that Hong-Amandel is playing a role because at each of the beam splitters that's inside one of the telescope receivers, there's at least a potential for a star photon to enter that beam splitter and a local oscillator photon to enter that same beam splitter at the same time. So quantum statistics does arise because they're bosons and because they're in identical temporal modes. they do show the interference effect. The difference here, I guess, is that in normal Hongo-Mandel, you want to have deterministically known one photon here and one photon here, both entering. Whereas in our case, we have these two separated in parallel and simultaneous Hongo-Mandel experiments going on, and this gives a rise to this fourth order interference between the two sides. And I should point out that this kind of effect was first predicted back in the 80s by two papers, one by Oliver and Stroud, and the other by Tan and Walls. It just hasn't been utilized very much.
Okay, thanks.
Like, I had a question, and this is something that I forget how the um exactly how the things scale, but there's a trade-off between the distance, the baseline, and the aperture that you need to collect from. Um, can you just reiterate a little bit about that, or I forget how the scaling goes for that?
Yes, this is a pretty subtle point and actually has important consequences for uh, astronomy. The simple way to think about it is that if you have a microscope and you're looking down in it, the greater the magnification that you dial in, the dimmer the object becomes, because you're simply looking at a smaller region of emitter and there's fewer photons coming from it. So by analogy to that, as you move the aperture of the two telescopes farther and farther apart, it's enabling higher resolution at the source. Therefore, by analogy, it's dimmer. Therefore, you actually need to have larger apertures. So you're not going to be using two fibers. You're going to be using, 30 centimeters or 1 meter telescopes to collect the light when they're far apart. And one more added point to that is you could then use an array of receivers. So instead of having just two, you could have six, and they could all be 30 centimeters. Like at the Chara array, they're 30 centimeters or 100 centimeters, I forget, but they're large enough to collect dim light. And then if you have more than two apertures, then there are new kind of protocols that have been developed. And then the question is, how can you use a quantum local oscillator to enhance detection of all those multiple apertures? And there are some recent papers being written on that topic.
Right. Yeah, thanks. Any other questions? Piotr.
Yeah, thank you so much for a talk. I had two quick questions. One is, can you estimate the impact of not having photon number resolving detectors in such a scheme?
Mm-hmm.
And the second question would be, I imagine that the photons that you're using in this interference need to be very much single mode. If they're not, does the visibility of the Hongo-Mandel-like interference drop down in a similar kind of like 1 over k kind of way? Thank you so much.
Yes, to answer the second question, the answer is yes. So we're careful to use single mode fibers everywhere to have spatial control. And as I said, you have to have temporal spectral purity, if you like. So when producing the heralded signal photon, it's important to design the down converter so that the idler and signal photon biphoton wave function is so-called separable. So that when you herald the herald photon, it heralds a pure state signal photon in a well-known wave packet. And then, as I said, you need to filter your starlight to approximate that same packet as closely as possible. If you don't do that, you lose visibility. But it doesn't go away immediately. It just lowers the visibility. So you can still deal with, visibility 10%. You could still measure that if you have good data. To the first point, see, what was the first point? Remind me.
So the impact of not using photon number resolving detectors.
Oh, yes, yes. So Matt Brown, who's a co-author on this paper, has developed a theory that goes beyond the simple Gottesman protocol. Gottesman assumed the star emits just one photon at a time. That's, of course, not true. So the star can emit multiple photons because it has thermal statistics. And And also the PDC source can emit, multiple photons. So normally the way you beat that is you attenuate everything down to such a low level that the higher photon number contributions are not significant. But then, as I said, the atmosphere changes, and then you don't have enough time to actually collect, a million pulses before the atmosphere changes. But Matt has analyzed all of this by generalizing the theory of Gottesman to include all these different effects. And there's a paper that he will be submitting very soon to show that. And the answer roughly is that PNR detection does help a lot in practical cases. But what would really help is if we had deterministic single photon sources like quantum dots that produced identical, on-demand photons at a very high rate to avoid some of those problems. But even then, since the star can emit multiple photons, having PNR detection does help a lot. So we're also looking into that.
Thank you very much.
Thank you. So I think, Juliet, you had come off camera. Were you looking to ask a question? And then if not, I will move to Rob. Okay, so Rob?
Yeah, thanks, Mike. That was a really nice and interesting talk, and very challenging work indeed. So if we want to make it more challenging, has anyone looked at whether we can do like multipartite entanglement, like the Chara setup has, would you say, 6 or 9, was it telescopes? Your single photon entanglement is really easy to generate multipartite entanglement. So could we benefit there? And has anyone looked at that? If there's a maybe practical advantage, it's not the right word, but
Yes, I believe so. If Matt Brown, are you here? If you want to comment on that, because I know there was work at Illinois and also at Rochester on the theory of that. Matt's not on board, it looks like.
okay.
I'm here, Mike. Sorry about that.
Oh yeah, they just got it. Okay, Matt, what you heard Rob's question? What do you think about that?
Yeah, so there have been a few. Well, I guess it depends what you mean by multipartite. Spatially, I don't think people have been looking past the case of 2 telescopes. I've done a little bit of work in that direction, but nothing serious at this point. A lot of people have been looking at doing, or at least a couple of people have been doing it mainly in the time frequency domain. So that was the case for Illinois. Also, I'm going to butcher the name, but Cavallini, that was at Harvard. They were looking at doing it, but in matter-based memories. Same thing with, I think, in Illinois. And then there's also a paper by Sam Dolinar from NASA that talked a bit more about these sort of multipartite spectral and temporal entanglement schemes.
is it multipartite entanglement or just multiplexing in time and frequency that they're doing?
Well, okay, that's fair.
I think noon states.
Yeah, they were looking at noon states. So,
but again, that's not necessarily multi.
Yeah.
Partite, yeah. So not much has been done to answer your question.
Yeah.
Okay.
Yeah.
I'm not sure I'm going to rush in and try and do it, but I was just curious.
Yeah.
Right.
Thanks.
Anybody else have an idea about that? There's a lot of experts on the call here. Does anybody know? Aziza, do you know?
Can I add something?
Yes.
Yeah, so just in terms of if you guys are thinking about a multipartite entanglement across more than 2 telescopes, which I thought what the question was about, I'm not aware of too many examples, but the work that Matt referred to from Harvard by Emil Habibulin, so there, in fact, there was multipartite entanglement distributed, but basically the idea there was that you would have multiple matter qubits per telescope, and then you would distribute multiple entanglement, like bell pairs.
Right. And then you would do quantum logic operations between the two telescope sites. Yeah, that's right. So it's a wide open subject, I think.
Sorry, guys, did I completely cut off mid-sentence?
Yes, you did. So
Yeah,
yeah.
sorry. Yeah, so all I was saying is that so there the number of entanglement distribution was basically to kind of improve the efficiency, because of one of the things, one of the reasons that work was done is to see can we do better than distributing like the exponential number of bell pairs, because like you kind of have to be simultaneous without the memory. And in fact, yes, you can use multiple bell pairs, and there the game was you can decode and encode information efficiently, so you can detect and then kind of process the information from the starlight later on, which gives you enhancement in terms of how many bell pairs you need to distribute per unit of time.
And I think in that case, am I right that they were storing up the star photons, not the local oscillator
Yes,
photons? Yeah. So
yes,
that's
yes,
different. Yeah.
that's right. Yes.
Somebody was asking if you could put a reference in the chat to that Harvard paper. Oh, somebody
I'm
just,
on my phone, so it will be a bit challenging, but
oh no, it
it's
looks like it's in the chat right now.
oh, amazing, fantastic.
Sam put it there. Looks like, is that the one? Yeah, that, of course, that's a very long-term futuristic idea, which is great because that's what we want to know. What are the ultimate possibilities? Okay, any other questions?
Mike, I've got a quick question. First of all, thanks for your talk. Really great. Yeah, I guess the question is, do you have an estimate for how long it'll take for your current experiment to be able to reconstruct the image from the star? Maybe you said I missed it, but yeah, about how long do you think it'll take, and what do you think it could be? Yeah.
Oh, okay. So I predict we're going to have one done within 9 months. However, the star of interest is called the sun. And we can do the sun with essentially without having large apertures because it's so darn bright. The next scheme would be to try to, oh, and also to do the sun, you only have to move the apertures a few millimeters apart. So we can do all that in our dome. But the next, if you want to do Betelgeuse, that's more challenging because then you have to move your apertures like, meters apart, up to 10 meters. And your apertures have to be, like 10 inches or 20 inches. So you need larger hobby telescopes and probably two domes. So I think that, something like that's going to require setting it up at a different location. So that could take, 3 to 5 years, I think.
Yeah, I guess my question is, once you're actually on, like, pointed at a star and collecting the measurements, how long, like based on the rates, how long do you have to collect data for it before you can actually reconstruct the image?
Oh, I see. Well, it can be done in a few hours. I have no doubt about that. But the bad news, again, is that you might as well use the direct method that Chara is using. They already do that, right? So if you're looking at Betelgeuse or Altair, they already have a system that works, and it works over large bandwidth. It's an amazing system because as the way they move the telescopes is not by moving the telescopes, they just let the Earth rotate, and that changes the relative angular position of each telescope relative to the distant star. So they just let it rotate over the day and they collect data. But then as the baselines change by tens of meters, they have large moving rails that are 20 meters long. And there's giant reflectors that move along these 20-meter long rails with sub-micron accuracy. It's an amazing scheme. So it's not really feasible to scale that up, beyond a few hundred meters. So if you want to go, 10 kilometers or even 1 or 5 kilometers, you're going to have to use fiber techniques. And then it's a whole different ball game. And then in order to beat the direct method, which does operate over large bandwidth, we're still going to need to have thousands of wavelength channels. So your question is a bit hypothetical. Once that's all set up, how fast is it going to work? I don't know.
Okay. Yeah. Thanks, Mike.
Can I also add a question?
Yes.
So we were also kind of exploring this telescope ideas with matter qubits here at Harvard. So I was wondering, in your opinion, kind of more of a futuristic question, what would be, do you think, like the best signal in the future for these protocols? So in principle, even if we multiplex, probably the bandwidth will still be narrow. So maybe it's some sort of like a molecular line. Is there hopes of detecting something like a signal, even if around like a bright star, but signal from a very faint source that actually truly will be interesting for astronomers?
Well, I think they talk about astrometry as opposed to astronomy. And astrometry means you're not trying to image a star, you're just trying to measure like some parameter, one parameter, like the diameter of a star or the separation of a binary. And in a case like that, it's easier. You don't need to really image everything. As far as looking at narrowband sources, I believe, Matt, you can correct me if I'm wrong, but I believe that the Stankus group at LBL, no, not LBL, BNL, Brookhaven, have actually done some prototype experiments looking at narrow line emissions from some stars, but I don't remember the details. However, there's another idea that was just published, I think, in PRL or Nature Science, published in the group of Janwei Pan, with a collaborator by the name of Frank Wilczek. Some of you have heard of him. And what they did was they illuminated a distant object with lasers. So from one building across the city to another building, they sent out laser pulse, which is narrow band, illuminated that object at a far distance, a target, and the backscatter then is narrow band. And they were able to image the object from the backscatter using a, not a quantum technique, but a classical technique. So I think as far as tabletop demonstrations, that might be the way to go. As far as astronomically important targets, I think that's really a hard question at this point.
So, and also the Jean-Marie Pan's paper was a intensity interferometry, right? They did like a 2-photon. Yeah.
Yes, that's
Okay.
right. But since they illuminated very brightly, then they could do that. Yeah, that's right.
Fair. I see. Thank you so much.
Yeah.
Great. Mike, I have one last question and then we'll wrap up. So you said that the first demonstration is measuring the sun and you'll have two telescopes millimeters apart with apertures. Our eyes are also more than a few millimeters apart. So do you think, you'll be able to beat the resolution, like at least in the prototype demonstrations of like what our eyes can do, or I assume that's possible.
That's
Like
a
a
good
first
question.
proof of
I never
principle.
thought of that question. Matt can jump in here. Of course, if you look at the sun with, through dark glasses, so you don't blind yourself, yeah, you can definitely see, you can definitely resolve the diameter of that object, no doubt. So I would say that you can't do any better than that if you don't move your apertures more than a few millimeters or centimeters. Is that right, Matt?
Yes, that's correct, Mike. For the demonstration, because we're only interested in effectively measuring the diameter, which is what you would do on a regular star, or at least that's like the first implementation of it. We won't have any more finer details than that, but your eye should be able to pick out some more fine details.
That raises a lot of jokes that you could make, like, do the eyes combine the light coherently? Is it a quantum processor? How do the eyes actually do it? What is stereo vision? Those are fun questions.
Let's get the biologist involved.
Right.
Great. Well, on that note, thank you everybody for coming. We're at the top of the hour. So in 2 weeks, we'll have our next tutorial, and it's going to be focused on more quantum information applications. So we'll be having Eric Chittenbar from the University of Illinois at Urbana-Champaign, along with Peter Bierhorst at the University of New Orleans, and they'll be talking about device-independent protocols and I believe some quantum position verification potentially. So, all right, we'll see you folks in 2 weeks and take care and hope everybody has a great rest of your day.